talking about the match control flow construct. Rust has an extremely powerful control flow construct called match that allows you to compare a value against a series of pattern and then execute code based on which pattern matches. Pattern can be made up of literal values, variable names, wildcards, and many other things. Chapter 18 covers all the different kinds of patterns and what they do. The power of match comes from the expressiveness of the patterns and the fact that the compiler confirms that all possible cases are handled. Think of a match expression as being like a coin sorting example. Coins slide down a track with variously sized holes along it, and each coin falls through the first hole it encounters that it fits into. In the same way, values go through each pattern in a match, and at the first pattern the value fits, the value falls into the associated code block to be used during execution. Speaking of coin, let's use them as an example. Using match, we can write a function that takes an unknown United States coin, and in a similar way as the counting machine determines which coin it is and return its value in cents, as shown here in listing 6-3. Okay, let's break down the match in the value in cents function. First, we list the match keyword followed by an expression which in this case is the value coin. This seems very similar to an expression used with if, but there is a big difference. With the if, the expression needs to return a boolean value, but here it can return any type. The type of coin in this example is the coin enum that we defined on the first line. Next are the match arms. An arm has two parts, a pattern and some code. The first arm here has a pattern, that is the value coin colon colon penny, and then the arrow operator that separates the pattern and the code to run. The code in this case is just the value 1. Each arm is separated from the next with a comma. When the match expression execute, it compares the resulting value against the pattern of each arm in order. If a pattern matches the value, the code associated with the pattern is executed. If that pattern does not match the value, the execution continues to the next arm. Much as in a coin sorting machine, we can have as many arms as we need. In listing 6-3, our match arm has 4 arms. Code associated with each arm is an expression, and the resulting value of the expression in the matching arm is the value that gets returned for the entire match expression. We don't typically use curly brackets if the match arm is short, as it is in listing 6-3, where each arm just returns a value. If you want to run multiple values of code in a match arm, you must use curly brackets and the comma, and the comma following the arm is then optional. For example, the following code prints lucky penny every time the method is called with a coin colon colon penny, but still returns the last value of the block 1. Okay, pattern that binds to value. Another useful feature of match arm is that they can bind to the pattern of the value that match the pattern. This is how we can extract value out of enum variants. As an example, let's change one of our enum variants that hold data inside it from 1999 through 2008. The United States minted quarters with different design for each of the 50 states. On one side, no other coin got state design, so only quarters have this extra value. We can add this information to our enum by changing the quarter variant to include a US state value stored inside it, which we have done here in listing 6-4. Let's imagine that a friend is trying to collect all 50 state quarters. While we sort our loose change by coin type, we will also call out the name of the state associated with each quarter. So if it's one of our friend doesn't have, we can add it to their collection. In the match expression for this code, we add a variable called state to the pattern that matches value of the variant coin colon colon quarter. When a coin quarter matches, the state variable will bind to the value of that quarter state. Then we can use state in the code for that arm, like so. If we were to call value in cents, coin would be something like this. When we compare that value which each of the arms, none of them match until we reach coin quarter state. At that point, the binding for state will be the value US state colon colon Alaska. We can use that binding in the println expression, thus getting the inner state value out of the coin enum variant for quarter. matching with option t. In the previous section we wanted to get the inner t value out of some case. When using option t, we can also handle option t using match, as we did with the coin enum. Instead of comparing coins, we will compare the variants of option t, but the way that the match expression works remains the same. Let's say we want to write a function that takes an option I32, and if there is a value inside, adds 1 to that value. If there isn't a value inside, the function should return the none value and not attempt to perform any operations. The function is very easy to write thanks to match and will look like listing 6-5 fn plus 1. Okay, let's examine the first execution of plus 1 in more detail. When we call plus 1, the variable x in the body of plus 1 will have the value sum 5. We can then compare that against each arm. The sum 5 value doesn't match the pattern none, so we can continue to the next arm. Does sum 5 match sum I y? Yes, it does. We don't have the same variant. The I binds to the value contained in sum, so I takes the value 5. The code in the match arm is then executed, so we add 1 to the value of I and create a new sum value with our total 6 inside. Now let's consider the second call of plus 1 in listing 6-5, where x is none. We enter the match and confirm. Compared to the first arm, it matches. There is no value to add to, so the program stops and returns the none value on the right side of arrow operator. Because the first arm match, no other arms are compared. Combining match and enum is useful in many situations. You will see this pattern a lot in Rust code. Match against an enum, bind a variable to the data side, and then execute code based on it. It's a bit tricky at first, but once you get used to it, you will wish you had it in all languages. It's consistently a user favorite. Matches are exhaustive. There's one other aspect of match we need to discuss. The arms pattern must cover all possibility. Consider this version of our plus 1 function which has a bug and won't compile. We didn't handle the none case, so this code will cause a bug. Luckily it's a bug Rust knows how to catch. If we try to compile this code, we get an error. Rust knows that we didn't cover every possible case and even knows which pattern we forgot. Matches in Rust are exhaustive. We must exhaust every last possibility in order for the code to be valid, especially in case of option. When Rust prevents us from forgetting to explicitly handle the none case, it protects us from assuming that we have a value when we might have null, thus making the $1 billion mistake discussed earlier impossible. Catching all patterns and the underscore placeholder. Using enums, we can also take special action for a few particular values, but for all other values take one default action. Imagine we are implementing a game where if you roll a 3 on a dice roll, your player doesn't move but instead gets a fancy new hat. If you roll 7, your player loses a fancy hat. For all other values, your player moves that number of spaces on the game ground. Here's a match that implements that logic with the result of the dice roll hard coded rather than a random value, and all other logic represented by function without bodies, because actually implementing them is out of scope for this example. For the first two arms, the patterns are literal values 3 and 7. For the last arm that covers every other possible value, the pattern is the variable we have chosen to name other. The code that runs for the other arm uses the variable by passing it to the move player function. This code compiles even though we haven't listed all the possible values U8 can have, because the last pattern with match all values not specifically listed. This catches all pattern meet the requirement that match must be exhaustive. Note that we have to put the catch all arm last because the patterns are exhaustive in evaluated in order. If we put the catch all arm earlier, the other arms would never run, so Rust will warn us if we add arms after a catch all. Rust also has a pattern we can use when we want a catch all but don't want to use the value in the catch all pattern. Underscore is a special pattern that matches any value and does not bind to that value. This tells Rust we aren't going to use the value, so Rust won't warn us about an unused variable. Let's change the rules of the game now. If you roll anything other than a 3 or a 7, you must roll again. We no longer need to use the catch-all value, so we can change our code to use underscore instead of the variable named other. This example also meets the exhaustiveness requirement because we are explicitly ignoring all other values in the last term. We haven't forgotten anything. Finally, we will change the rules of the game one more time so that nothing else happens on your turn. If you roll anything other than a 3 or a 7, we can express that by using the unit value, the empty tuple type we mentioned in the tuple type section, as the code that goes with the underscore arm. Here we are telling Rust explicitly that we aren't going to use any other value that doesn't match a pattern in an earlier arm, and we don't want to run any code in this case. There's more about pattern matching that we will cover in chapter 18. For now, we are going to move on to the if-let syntax, which can be useful in situation where the match expression is a bit wordy. Okay, the if-let syntax lets you compile the if and let into a less verbose way to handle values that match one pattern while ignoring the rest. Consider the program and listing 6-6 that matches on an option u8 value in the config max variable but only wants to execute pattern if the value is the sum variant. If the value is sum, we print out the value in the sum variant by binding the value to the variable max in the pattern. We don't want to do anything with the none value. To satisfy the match expression, we have to add underscore arrow and rounded bracket after processing just variant, which is annoying boilerplate code to add. Instead, we could write this in a shorter way using if let. The following code behaves the same as the match. Okay, the syntax if let takes a pattern and an expression separated by an equal sign. It works the same way as a match, where the expression is given to the match and the pattern is its first term. In this case, the pattern is sum max and the max binds to the value inside the sum. We can then use the max in the body of the if let block in the same way as we used max in the corresponding match arm. The code in the if let block isn't run if the value doesn't match the pattern. Using if let means less typing, less indentation, less boilerplate code. However, you lose the exhaustive checking that match enforces. Choosing between match and if let depends on what you're doing in your particular situation and whether gaining consciousness is an appropriate trade-off for losing exhaustive checking. In other words, you can think of the if let as a syntax sugar for a match that runs code when the value matches one pattern and then ignores all other value. We can include an else with an if let. The block of code that goes with the else is the same as the block of code that go with the underscore case in the match expression, that is equivalent to the if let and else. Recall the coin enum definition listing 6-4 where the quarter variant also holds a US state value. If we want to count all non-quarter coins we see while also announcing the state of quarters, we could do that with a match expression like this, or we could use an if let and else expression like this. If you have a situation in which your program has logic that is too verbose to express using a match, remember that if let is in your Rust toolbox as well. We have now covered how to use enums to create custom types that can be of one set of enumerated values. We have shown how the standard libraries option type helps you use the type system to prevent errors. When enum values have the data inside them, you can use match or if let to extract and use those values depending on how many use cases you need to handle. Your Rust program can express concepts in your domain using structs and enum. Creating custom types to use in your API ensures type safety. The compiler will make certain your functions get only values of the type each function expects in order to provide a well organized API to your users that is straightforward to use and only exposes exactly what your users will need. Let's now turn to Rust modules.